Here I'll talk a bit more about how the monitoring stations can be built up into networks for air quality information systems. And I'll start off with examples from outside of our region. And first, if you think about managing environmental issues, one of the pieces of good news about air quality is actually that air pollution is not a permanent problem. If you get rid of biodiversity, if a species goes extinct, it's gone forever. But with air quality, you cut down on the sources and the problem starts going down. And it's actually been done before in a lot of places. This picture is Los Angeles, California, which was the first major city in the world that really did a huge effort to tackle an air quality problem. It's the second largest city in the US, and right from its design on has been very heavily dependent on automobiles. It's located between the sea and the mountains, with the wind blowing from the sea towards the mountains, so the pollution gets trapped against the mountains. And it's been basically a world leader in testing out various ways of addressing air quality issues. Already in the 1940s, they banned garbage fires, and at that time they didn't have any other way of measuring air pollution, so they measured dust fall. How many grams of dust were falling, or what they call dust and smoke, were falling onto a square meter of surface. It was the first place in the world to require catalytic converters in cars, already in the 1970s, and has one of the best monitoring networks in the world, with more than 100 stations in the Los Angeles basin area. But even as the population, the economy, and the vehicle numbers have increased, air pollution has steadily improved over the last few decades in Los Angeles, actually. If you're trying to find an inspiration for Kathmandu or cities like Kathmandu, though, maybe Los Angeles is too rich, too different. And maybe there's another place we could look for that seems to be almost a sibling of Kathmandu. The picture down there is not Kathmandu. It's another place in the world. It's a historical capital city in a relatively poor country with limited resources, a large poor population that is migrating to the city, a growing vehicle fleet, actually also a flat bowl-shaped valley that's surrounded by mountains that was once a former lake, in an earthquake zone, with most of the houses made of bricks, with a lot air pollution layers trapped by inversions, and with the air pollution blocking the view of snowy peaks. This is how view out the 20th story window looks in Mexico City. It's quite a lot bigger than Kathmandu, but still shares a lot of similarities. Typical houses, street markets, street scenes. 25 years ago, Mexico City had the worst air quality problem in the world. Ozone was exceeding WHO standards 90% of the year, and 70,000 people per year died of respiratory illness directly related to air pollution. And there was serious discussion in the government about flattening some of the mountain peaks around Mexico City and installing large fans to blow the air pollution out. Today it's still very polluted, but actually much more livable, and pollution levels are often below WHO standards. Here's just some time series over the years of ozone, NO2, CO, SO2, between 1986 and 1998, and you see relatively rapid drops. How was the cleaning up of air pollution achieved? Mostly through policy interventions. They shut down an oil refinery within Mexico City, introduced low sulfur diesel, unleaded petrol, which cut down on lead, and then catalytic converters, which cut down on carbon monoxide. They moved industries out of the city, out of the valley, and have been doing ongoing improvements in fuel standards, imposed certain restrictions on private vehicles, greatly improved inspection and maintenance of vehicles, and focused a lot on the big emitting vehicles that are operating all day long. So 2,000 city buses and all old taxis were replaced. They introduced larger size microbuses and expanded public transport, metro, bus rapid transit system, bike lanes. This is the smallest size bus in Mexico City now. They have a metro rail system that's used by a few million users per day. It was not built in a day or a year or even a decade. They've been building it since the late 70s or so. Build safe bike lanes, and people are willing to use their bicycles. And Bus rapid transit system, they now have 4 lines. This has been mentioned several times over at the EST forum already. It's a way of using buses in a much more efficient way and almost using buses like the way trains would be used, where people pay to get onto the platform. The platform is the same height as the bus. And so people board the bus from the same level as the bus, through all doors, already having paid. So the bus has to stop much less time at the station than if individual people were going in and out the doors, paying while they're getting in and out. And then the buses are on separate lanes. So the buses can go much faster. But very important in Mexico City's reduction of air quality has been air quality monitoring, which first started in the 1960s with some instruments that are now museum pieces. Their current network has been set up since the 1980s, and they have 29 state-of-the-art stations that transmit live data, provides information to the public about health and safety, and feedback to policymakers about whether policies and enforcement are effective or not. Here's a visit to the city center station on top of a government-run high school. The station is here on the rooftop, and I'll just give you some sense of what it's like to go visit the station there. It doesn't need a fancy building or fancy location so much as a useful place. So walking past classrooms, I visited on a holiday, so there were no students there. And then through the bathroom, squeezed through a little door to the backside between 2 bathrooms, between the flush tanks. And they put the flush tanks on the other side of the wall for easier maintenance. And then you see a ladder back here, out through a hatch onto the roof. And then you come out onto the roof, and here's the air quality station. And with probably $200,000-$300,000 worth of state-of-the-art instruments. This one, okay, here's measuring ozone, NOx, SO2, CO. This is the back of the instruments. So a lot of these instruments can be mounted into server racks, just like computer equipment. And what we showed you before was also some of it could be put into server racks. The gas analyzers for Kathmandu and Thimphu are not here yet, but we'll have fairly similar instruments. Here's the instrument they use for PM 2.5 and PM 10. It's a thermotium, which uses a microbelt. Here's their 30-minute, 1-hour, 8-hour, 24-hour, 12-hour, and current readings. PM 2.5, PM coarse, which is the difference between 2.5 and 10, and then PM 10. And here are the filters from inside the instrument. I'm showing these because, so these are the filters that measure where PM 10 accumulates, and these are the ones where PM 2.5 accumulates. What do you notice? Apart from the size of the filter, which is irrelevant. What do you notice about the color? Yeah. So why would that be? Black. Yeah, there's a lot more black carbon on this and a lot more dust on this filter here. And black carbon, which is what you get out of diesel and brick kilns, is much finer. It's finer than PM 2.5. So PM 2.5 has a much larger fraction black carbon. Then the staff at the station maintain a detailed logbook, both an electronic and a handwritten one. They sign everything. They make sure they've checked everything. In order to get good data, you need to make sure that the data is well managed. With 29 stations, there's a lot of repair work to do. So they have a central lab where they bring instruments back for repair, where they have spare instruments that are swapped in to the stations, and which is the base out of which they operate. They also, I showed this picture before. The mobile van was actually self-built by the staff there using an old truck. And what happens to the data? It comes live into a control center at the mayor's office. And so throughout the day, there are people sitting here watching the data from different instruments. They're also seeing whether the data, they're getting instrument diagnostics, are the instruments running well or not. If there's a problem, they immediately call the technician to go check. And then if there is an air quality problem, if air quality is really bad, the information gets distributed via radio, SMS, websites, Facebook, Twitter, even a children's website. Mexico City used to have a lot of really bad air quality emergencies where air pollution was so bad people were asked to stay indoors and close their windows. On their website, they have an air quality index. Sorry, this is in Spanish, but green is very good, yellow is okay, orange is bad, red is very bad, purple is really bad. And they translate each of the units for each of the different pollutants into this kind of index, the IMECA index, and they just report that to the public. It doesn't matter whether from PM10 your cutoff for is 120 and for ozone it's 80. They just translate everything into a scale. Where 0 to 100 is okay and above 100 gets bad, increasingly bad. So the public just has to deal with one number and no units for different pollutants. And for any of the pollutants, if IMECA is 100, then it's bad. And so what they're reporting here is the hour of the day from 1 a.m. until 5 p.m. Northwest, northeast, center, southeast, southwest of the city. And you see air quality in the afternoon here for ozone is getting worse. And PM10 here in the northeast has been bad throughout. A bit late, and then they also have a map. You can click on a place and it tells you what the IMECA scale is. And then a children's website for children to learn about air pollution, to learn about is it good, is it safe, should I go outside or not, what is the weather like. So what happens on a bad day when IMECA is high? There are rules in place that if IMECA crosses certain thresholds, these and these factories have to shut down. Then vehicles older than a certain number of years are not allowed on the road anymore. And schools know that they have to cut down on children's outdoor activities. So the monitoring network helps assess the impact on population exposure and also the effectiveness of the policy. If you shut down the factory and nothing happens to the scale, to the pollution you're measuring, then maybe you're shutting down the wrong thing. And just to give you a sense of the running budget for that, so running those 29 stations, their annual budget is about $300,000, which given the level of equipment they use is actually very cheap, and it's much cheaper than places like Los Angeles would be, or even I think what Delhi is spending for similar instruments. And part of the way they keep costs down is by sourcing the parts of the instruments directly from those who manufacture it. All these instruments have pumps in them that pull air through. The companies that build the instruments don't build the pumps. They buy the pumps from somewhere else and then mark it up. So don't buy the pumps from the instrument manufacturer. Buy it from the company that builds the pump. If the rubber inside the pump is broken, don't buy the rubber from the company that builds the pump. Buy it from the rubber manufacturer. Things like that. So they've traced back through the supply chain and figured out ways to cut costs. A lot of other countries also have these air quality indices. The US has had one for quite a while. And then here's how it translates. See, for ozone, up to 54 parts per billion is good. For CO, up to 4.4 parts per million. See, for each of the pollutants, the scale is different, but it gets translated into this air quality index. So this is what the public needs to know. India has an air quality index as well, with slightly different scales, as does China. So this is what I just pulled off the website an hour or two ago from Beijing right now. So here you have the air quality index in different parts of the city where their monitoring stations go. And actually this AQICN website tries to pull together monitoring data from wherever it has access to live data. I want to go back briefly to this table here and check on if these units up here, ppb, ppm, microgram per cubic meter, do these make sense, or do I need to explain these?
And then what's the relationship between ppm and microgram per that?
When you have a gas, you can compress it or expand it somewhat, right? And so if you take the same volume of gas at sea level and you lift it to the altitude of Kathmandu or the altitude of Thimphu, if the same number of gas molecules, you occupy a bigger volume because the air pressure is lower, so the gas gets wider. If you release a helium balloon here and it goes up into the atmosphere, it actually grows a bit bigger. So with gases, often the units we use is something more like a percent, okay? What a percent is how many out of 100. So do you remember what percent of the air is nitrogen? 78% or so. Oxygen?
21.
about 21%, okay? So you have percent, right? Have you ever seen a unit that looks like this? Per mil, which is per 1,000. So 21% will be 210 per mil, right? But a lot of pollutants are present at much less than 1 in 1,000. Even carbon dioxide is present in much small, is smaller than 1%. So people use the unit per million. As are parts per million. So what's 21% in parts per million? So 21%, that would be 21 over 100, right? Can you see? So in over a million, $210,000, right? That would be 21. Does that make sense? Okay. So carbon dioxide is present somewhere around 400 parts per million. Only. That's a much less than oxygen, right? Then if you want to go for things that are present even less, you use the unit parts per billion. So we call it ppb. So ozone would be in 40, 50, 100, 150 parts per billion. So the question was, how does that relate to micrograms per cubic meter? Even gases have a certain weight, right? So if you take the air in 1 cubic meter has a weight of maybe about 1 gram or so, if you could weigh that. So if you have a certain volume of air, let's just say cubic meter of air, say like, this thing like a cube here, right? The weight of the air in there is about maybe about 1 gram. But ozone is only a very, very tiny fraction of that. So it could be maybe a microgram or less than a microgram could be the ozone in there. The reason for gases we prefer to use parts per billion or parts per million as units is that when you take the air in here and you let it expand or compress, you change the weight per cubic meter, but you're not changing the ratio of your gas to other things. So you see here, for ozone, the unit is parts per billion, PM2.5, which is particles in the air that are suspended in the air. There the mass makes sense to measure the weight. PM10 also, and then the gases again are in parts per billion. Another quick terminology you've been hearing, whereas like greenhouse gases and Bidya mentioned short-lived climate pollutants. Greenhouse gases are the gases in the atmosphere that create warming of the atmosphere, that contribute to global warming. And then you might come across the term SLCP or SLCF, short-lived climate pollutants or short-lived climate forcers. And it's a bit of an artificial category. It's things with a relatively short lifetime in the atmosphere that contribute to changing the climate. So black carbon particles, they have a lifetime of a few weeks in the atmosphere. But as you've been hearing and seeing, they warm up the atmosphere. They have an impact on the climate, right? Ozone and methane, both are gases that are actually, they're greenhouse gases. but they have a short lifetime. Methane about a year, ozone depending on where you are, a few weeks to 2 months, 3 months or so maximum. And so they're also often considered short-lived climate pollutants. And then hydrofluorocarbons, which are some of the substitutes and substitute refrigerants to CFCs. They also have a short lifetime and they contribute. So it's a somewhat artificial category, but this word gets thrown around, so I wanted to make sure that you were familiar with it. All right, thank you.